Welcome, everyone. Thanks for joining our session. My name is Sandra Zaki, and I'm presenting today together with Luca Valentino, SCOR's non-life risk modeling application running on Databricks. Just very quickly, so who are we? We work for SCOR, which is a global reinsurance company. It has a few thousand employees and 3,000 offices around the world. We are actually located in Switzerland. So in case you're not familiar with the reinsurance concept, so reinsurance is a company providing cover to other companies, mainly primary insurances. So a primary insurance is a company where you usually go and get, as a normal person, your insurance for house and motor and car and stuff like that. So SCOR launched recently its latest strategic plan called Quantum Leap, which has this time a very strong technological focus, and this project was realized under this strategic plan. So what are we going to talk about today? We want to give you a brief introduction about non-life risk modeling. Then we go a bit into more details of the replatforming. So what did we do? What was the reason? And we give you then finally a bit of a technical approach, so technical insights about how it was done, and finally a small acknowledgement to a lot of people involved in that project. So the non-life risk modeling, here it's more an illustrative overview of certain risk contributions. So the term non-life is also often referred to as P&C or property and casualty, so that you just have heard the term here. This makes the term non-life a bit more concrete. So property means everything which is a physical good, like a car or a factory. Also very big things like ships or whole construction sites. And casualty here means casualties which are liability related. So an example would be if you produce a certain medical device which has a flaw, has a design flaw and kills people, these casualties are here meant. So this is a liability-related casualties. So here in the upper left corner, we have the natural catastrophes, or in short, NatCat, how we call them. This is more or less the textbook example of reinsurance. So you can think about a primary insurer. If you insure houses and property in Florida, you most certainly need a reinsurance cover against very big NatCat events like hurricanes and earthquakes. Then if we move from the NatCat down to motor or car insurance, and here in this example, this is more a traditional line of business, I would say. You can think about it that it's everywhere more or less the same, like the cars are the same, the rules are the same, the issues are the same. And this risk universe is actually very dynamic, so it's also expanding. If we go to the right, to the cyber risk, this is actually a risk which was introduced very recently. It's actually very new risk compared to motor and NatCat risks. So here, if we zoom a little bit out of the non-life view and look at the broader risk landscape, which we model at SCOR, and it's called simply internal model. We are at the reddish pinkish box here, Norma, which is simply non-life risk model aggregation. If you move 2 boxes up, you have the life, which is actually the complement of non-life. So this deals with everything: life insurance, health insurance, critical disability, critical illness, stuff like this. And other risks which we have in the internal model, the typical things that you find in any financial internal model, like credit risk, asset risk, op risk. Now, I want to briefly talk about the feeding systems for the non-life risk model aggregation. The bottom, the SCOR business solution pricing and the P&C treaty pricing, this you can think about 2 categories of products. So here we get the information of what are the risks we're covering for the clients in the future. The reserving is actually all the risks which we covered in the past from the clients, which still have uncertainty and therefore risk. And the NatCat is also modeled outside. Actually, there is a whole industry providing tools for modeling NatCat events. So they really model the underlying physics. So it's not strictly a financial model. So if we now be a bit more specific and zoom in into one of the non-life risk model processes, basically the aggregation. This is actually the step which gave the tool its name. So it's a non-life risk model aggregation tool. And I want to briefly explain to you how it's working. If we start at the very bottom, you see treaties. This is actually all the risks we covered for the client. So it's single contract level. They are grouped in certain baskets. And you can think about that. We have tons of these baskets. And now in these baskets are located in different branches of a hierarchical tree. So the branches represent the dependencies which you would have between the baskets. So as you move up here, you apply dependencies between portfolios. So you can also think about baskets as small portfolios. So if you move up the aggregation hierarchy, you apply dependencies between the portfolios, you gain diversification, and then you move up until the very bottom, until the very top node, the non-life, where you are then finally an internal model, and non-life risks get diversified here with other risks. So conceptually, the baskets, we do Monte Carlo simulations, so all the portfolios or the baskets at the bottom are independently simulated. Then you move up the hierarchy, you apply dependencies, you gain diversification, and at the very top you have a fully diversified scenario consistent view. Okay. Now I want to talk about the replatforming project. So what did we do and what was the reason to start this? So we had an original application which was doing the aggregation, which we discussed quickly. Also, there were tons of other things doing. So there was a lot of evaluation, tons of reporting on top of it, which was, I would call it a typical business application. It was written in C# and more than 10 years ago. It has grown to over 100,000 lines of code. And it has also there was a lot of stuff added, which made the runs slower and slower. So we increased the machine. So as we increased the model, we increased the machine. Until now, we had a fairly big server, which was running here 24/7, of course. And here we got in this threshold that if a user would need an extensive model with some extensive reports, he had to wait the whole working day. Basically, he had to come back the next day. Even if you had long working hours, you had to come back the next working day. So and during this run, all other users would also be blocked. So he would block the whole machine for more than one working day, which is very inconvenient. Then as more users want to run more stuff, so we decided to completely replatform this application. Also, we had the typical problems due to legacy code, so it was hard to maintain. It was easily breaking. The test coverage was low. So the requirements for the replatforming of this application was we wanted a fast and efficient backend calculation, obviously, but also we wanted to have scalability. So different users should not be blocking each other. So there should be dedicated computing resources for different users. And also for one user, the system should dynamically scale for a user running small things or running very big things. Then we had to recreate all the standard reporting because the model had standard reporting for different stakeholders. They needed to be really replicated one-to-one. And on top, we wanted to add a end user computing capability. So when the original application was designed, nobody envisioned that 10 years later, really business people want to interact dynamically with the data. That's how we decided to use big data technology for replatforming this project. So we have chosen Spark as a computational framework and Databricks as a service on top. Databricks offered here a lot of things which we would already easily need and we were looking for. So all the Spark versioning was taken care of. We could easily deploy our application with a Docker container. The security was taken care of by Active Directory support. And with the notebooks, together with the SQL analytics, it was the perfect end user computing thing which we could give to the business users so they can interact with the data in a more dynamic way. So I want to hand over to my colleague, Luca Valentino, who will tell you now what came out and how did we do it. Thanks a lot.
Hi all, I'm going to take over from Sahand and I'm going into a bit more details. So we're first going to tell you what we achieved with the replatforming project. So we had an old application which was based on the .NET. It was running on a premise server, which was like a 32% 384 gigabyte of RAM, and then code was optimized and still to do some parallelization at low level, but still quite optimal, I would say. We had a shared memory architecture. The data model was based on blobs. I mean, let's say for the big data, we were saving data in an Oracle database on blobs. And for the input data and metadata, we were just using plain SQL tables. The application, there was almost no scalability because of the architecture and many different problems related to the architecture. So because of this, the processing time was quite long and RAM consumption was very high. It was 300 gigabytes for each model run. So the users were basically blocked. They could not run anything in parallel, only one model run per user. The data storage was very inefficient because of the large amount of data was saved, as I was mentioning, into SQL blobs, and the read and write time was taking really too long. Therefore, we had one single model run taking several hours, and users waiting, actually one user waiting for the model run to be finished. Actually, like the day after one day, and the day after still they had to run additional reports. So it was like a long time process for running the model. Where we were also limited to 100,000 simulations, and in addition to that, the application had only. I mean, there was only one version of the application which could have been deployed to QA and production. And the deployment was also a bit painful. There's the old-fashioned way, and nothing which has to do with DevOps practices. So code change on the top of all these problems. We had code change were really hard to make due to legacy code. The application was really rigid and fragile. There were not so many tests, as Sam was explaining. Our test coverage was very low, and it was really a pain to change the code. So we went from this paradigm to a new one, which is from the on-premise and .NET and all this shared memory architecture to a Python PySpark-based application, which is running on Azure Databricks now with on-demand Elastic clusters. So we can achieve massive parallelization thanks to Spark. We can parallelize and achieve horizontal and vertical scaling. We can save everything in delta tables now, and that's what we use as a storage model. The Databricks cluster scaling is also dynamic, so we usually set up the cluster so that we go from 5, 10 or more to 20, 30 or 40 nodes. And Databricks decides how to scale out with a number of nodes. So with this system now we can implement more complex algorithms, and we did already implement very complex things which were impossible to implement with the old system. So we have a very efficient I/O with delta tables. We store about 25 gigabytes per model run. The model run is way faster. It's 10 times faster than the previous one. The additional reports, they are not comparable at all. I mean, they are more about 10 times faster on average, and all of them. But some of them they're really extremely fast compared to the previous application. So we have 1 million simulations, but we are not limited to 1 million. We could still leverage from the scaling out, and go even to 10 million if we want. So model runs now are possible. We can run them in parallel. There is a multi-versioning system which is allowing the users to test many different versions on QA and also production to run different versions at the same time. We can deploy, thanks to Azure DevOps, in few minutes all the components. We have no legacy code, and the modules are basically now. The application is built in such a way that it's everything is so modular, which is very easy to extend, and it's very easy to test. So in the future, what I want to mention that we would like also to leverage from Photon, from the Photon framework and the GPUs. We already started investigating this. We are at the moment waiting for the next releases because of there are some limitations at the moment. Yes, we are looking forward actually to jump also on this new technology and see and leverage from this. So the next slide, I would like just to focus quickly on how we organized this project and how we could make it operative. So we had a small development team. We started with this small development team in 2018. We finished the project last year, about end of September, beginning of October, officially. But since then, we continued developing a lot of new features. So the project is in collaboration between IT and SCOR PNC. We adopted offers an agile approach. We are using Scrum, which is a mix of Scrum and Kanban. On the top of this, we added a lot of extreme programming engineering practices, like test-driven development, refactoring, pair programming, trying to keep the design simple, having coding standards, and going to continuously integrate and having small releases. So the whole framework is really like a software engineering framework which we adopted for the development. And on the software engineering side, we have a system which is mainly object-oriented. Functional programming, of course, is used mainly within all the classes objects. We adopt a clean code, and we use code as documentation. We decided, since it's an internal project, we're not writing the documentation to focus on the code. We also implemented design patterns to facilitate the implementation. We try to be solid. We use architectural patterns. The application is domain-centric. We use encapsulation and continuous design. On the DevOps side, we use Azure DevOps to basically do all the development and operational. We have the repos, pull requests, we have all the backlog management support, and all the CI/CD pipelines. Something very interesting, which is a bit particular in our project, the CI pipelines for the Spark for the Spark test, unit test, and the regression test, they spin up Databricks clusters so that we can run the test on the cluster and jump back and basically get the results directly from the cluster. So next is a quick overview of the system architecture. I will go quickly through that. Basically, now the user has the possibility to go through the user interface, set up its model, go through the input data, do a data validation, store this data, which are stored still in the Oracle database. And once the model is ready, they can basically click a button, run the model. The system is communicating via an interface, which is a web application, with the backend. And the backend is basically grabbing the package which we deployed through Azure Container Registry. All the artifacts and the Docker image are basically pushed there. So we grab them, and there is an Azure Data Factory as a job orchestration for all the pipelines, which is then basically spinning up clusters for each pipeline on Databricks. Databricks does all the computations, the ETLs, the simulations, and storing everything in the Azure Data Lake. And then from the data lake, we can still pick up all the results and do additional reporting. So the additional reporting is done through notebooks and other reporting tools. We have a reporting tool. And so the user can go back also to Databricks, get into the notebooks, and grab the data and do additional analysis, which it's basically what Sam was saying at the beginning, where there is an end user computing functionality, which is facilitating the reporting for the users. So we jump on the next slide, which is the technical approach we adopted. So this is a very simplified version of what we do in the application. It's extremely simplified, but it's just to give you an idea of what we do in terms of steps. If you look at the top of the slides, you have the model steps. In the middle, there is like a representation, a graphical representation of them. And at the bottom of in the technical approach, I'm trying to describe what we did in terms of what we used in terms of technology and what approach we used for implementing this. So we have the first model step is we have all the input data which are basically probability distributions which are inputted by the users, and these distributions are used to do Monte Carlo simulations. This Monte Carlo simulation is a 1 million simulation for all the segments modeled by the users. For each segment has 3 probability distributions from premium, losses, and expenses. And there, what we adopted is actually an approach based on NumPy and RDDs. By using jumped and random number generators and NumPy, we could achieve the parallelization. And the RDDs were helping us basically to transform, let's say, to go from the input data, which were not Spark-based or data frames, to the data frame. So after this step, we have everything in delta tables. We can load the delta tables, and we do, for instance, for the copula-based dependency model, which is nothing else than taking these distributions and creating dependencies between the distributions. We basically we start using only Spark data frames and SQL operations and Pandas UDFs, and as well just pure UDFs and Windows functions. Everything gets saved again into delta tables, and the evaluation process, as well as for the reporting, we only use data frames, Pandas UDFs, Windows functions, and delta tables mainly. This is more or less the picture. Of course, there are tons of other things this is extremely simplified, but this is just to say that we start from an RDD approach just because our data doesn't allow to jump directly into delta tables. And then from that first step, we move to a more efficient way of using Spark, which is based on Spark data frames, UDFs, Pandas UDFs, and Windows functions. So I'm actually at the end of the presentation. What I would like to say. So as last slide, I would like to thank you, the core team. We had many people, many contributors, actually, which I would like also to thank. They were jumping in at the project and jumping out, so there were many people contributing. Our core team is now what you see in the central part, and I would like also to thank you also to all the product owners. They had to wait quite a lot of time to get the project done. Thanks actually for trusting us. And a special thanks goes actually to Martin Studer from Mirai Solution. He was, and he is still our Spark guru, who introduced us to the Spark world and pushed actually the project to the actual status. So thank you for listening. I hope that was interesting for you, and I wish you all a great day. Bye.